Good morning, everybody. I'm Dr. Stuart Morris from Pentaxia, the engineering director, and this is Albert GIBBS. He's an engineer with Pentaxia. Today we're going to present self-curing isothermal composite tooling for low energy and large-scale applications. So I'm going to ask you a few questions. I'd like a bit of crowd participation on this bit. I know it's not exactly full today, but your help would be appreciated. So hands up if you would like to make composite mold tools and components larger than your autoclave allows. Anybody? That's good. Yeah, thank you very much. Albert? Yeah, Albert's in. That's good. Okay, put your hands down, please. Okay, next up, question 2. Put your hands up if you would like a mold tool where you can control the surface temperature incrementally to account for exothermic reactions in large, thick laminate sections. Good. Excellent. Thank you very much. Okay, our third and final question. Put your hands up if you'd like to save a significant amount of money and you'd also like to massively reduce your carbon footprint on every component cure. Very good show of hands on that one. So just to recap, we'd like composite tooling with the ability to make larger components than our autoclaves allow, be able to modulate the cure temperature to avoid potential exothermic reactions, to reduce the cost by a significant amount, and also to reduce our environmental impact. Today, we're going to disseminate our EcoTool project, which is part of the National Aerospace Technology Exploitation Program. It's a grant-funded program, and we'll provide some solutions to our needs. Our project partners were the Advanced Manufacturing Centre in Sheffield, UK, and our end users were BAE Systems. In this presentation, we will discuss a little bit about Pentaxia and the AMRC to give context, the shortfalls we've identified with the autoclave process. We'll provide details on the EcoTool technology, and we will look at the results of the project, and we'll discuss what's next. Can I have my video, please? Okay, so Pentaxia, we're a family-owned business, started in 2008. We have a 7-acre site with a 70,000 square foot facility. We have 150 employees. We're based in Derby in the UK. We're just running through some of our capabilities here, but we've got these on another slide anyway. Can my video stop at all? We've got problems. Can anybody stop my video? Okay, it appears the video is playing out quite a bit longer than we expected. There we go. Thank you very much. Okay, so we are a DFM, and we also have partners with FAA facilities, so we can carry out design for manufacture. We have we have 4 in-house tooling designers. We have 2 3-axis and 4 5-axis CNC machines. We machine tooling boards, metallics, foams, and also composites, from which we make patterns, mold tools, jigs, and fixtures. In terms of our process capabilities, we have 2 top-of-the-range Zund kit cutters. We have 4 autoclaves, the largest of which is 4.5 meters long. We have 5 heated composite presses. The largest platen is 2 meters by 1.5 meters. We have 2 paint booths, both of which are 5 meters in length, a 7-meter surface table, and we also have a 3-meter CMM machine that we do for automated inspection. Our partner, the AMRC, is a research technical organisation based in Sheffield in the UK. The AMRC bridges the gap between academia and industry, assisting companies like ourselves to deploy new technologies onto the market. Unfortunately, Ollie and Anthony couldn't be with us today. So let's look inside the autoclave, the go-to process for aerospace composite components. So what's good? It's a well-proven method. It has a uniform temperature control. The pressured environment gives good consolidation and a low void count. But what can be improved? Autoclaves are expensive assets to buy and run and also maintain. The size of the autoclave limits the size of the components that we can produce. They take valuable floor space when not in use, and they can't control the exothermic reactions within the thick laminate sections due to their uniform temperature. As part of the Paris Agreement, which we are in Paris, the countries around the world have agreed to reduce their global emissions by 2050. The manufacture of composite components is energy intensive. A typical 4-meter long composite component cured in an autoclave uses 400 kilowatt hours of energy, costs around £186 in energy just for the heating alone, and releases a huge 88 kilograms of carbon dioxide.
Morning. Thank you for coming to our presentation here. I'm Albert Gibbs. I'm the engineer that's been managing this program over the last about year and a half or so. So I'm just going to tell you a little bit more about EcoTool, about the technology, and about what we've been doing here. So on the side at the moment is one of our large composite presses. And what makes this interesting is the heating method that it's used to heat the upper and the lower platen. It uses resistive heating. So resistive heating is really simple. It's passing a current through a resistor and generating heat. It's what heats up our electronics, like phones, laptops, why we've got fans and computers, all of that kind of thing. It's generally quite a negative effect. We want to remove heat. But with EcoTool, it's actually the backbone of the technology. It lets us do something called direct heating. So direct heating of our mold tool gets us away from needing an enclosed chamber like an oven or an autoclave, because instead we can just heat the mold tool up. And we get away from the inefficiencies that are associated with using air as a transfer medium for temperature. Because of that, we can start to tackle some of the sustainability challenges that Stu mentioned earlier. So direct heating has some challenges, and a lot of those revolve around the heater elements that are used to create that resistive heating. Traditionally, heater elements are stiff wires. An example, this platen that's here, the elements are sort of 10 mil by 10 mil square section. There's really no way to get that to conform to the intricate tool surfaces that we see come in on like a day in and day out basis. So we've done something a little bit novel with the heater elements. Now, this is based off research from Matthew Conson on a project called the Maestro Project. And what it does is really utilizes the conductive capabilities of carbon fiber to be our heater element. So this is something that's never been done in tooling before, and it removes the design limitation of having to have thick or non-conforming heater elements in your composite tooling. And we see this as a push to the industry to try and incorporate more out-of-autoclave processes. It's only been a short program, but we've seen some really, really positive results from that. Now, I think it's pretty safe to say that the composites industry is well-versed in handling carbon fiber. I'm pretty sure all of you, or almost all of you here, have been hands-on with carbon fiber and manipulated the material. And this also goes to all of our laminators and people who have made it more than just a job, but a skill in handling and manipulating this material. So using carbon fiber as our heater element really makes use of that skill that's already baked into the industry. It lets us create heated tooling that is cheap, quick, easy to implement, and doesn't require a lot of upskilling of staff to convert what would be a traditional composite tool, say a 1/8 laminate, so 1 lightweight ply, 8 heavyweight plies, 1 lightweight ply, into a tooling laminate that can be heated. Also, because there's no exotic plies sitting in your tooling laminate, you greatly reduce the risk of warpage or delamination or any other kind of damage to your tool as it's going through further heat cycles when you're curing components. Now, I mentioned earlier, this has been quite a short program. We've done some heat cycling on the tools that we've done and seen absolutely no issue with warpage, falling out tolerance, anything like that. But as you see when I come into kind of the future steps, one of the big points will be doing more thermal testing on our tooling. So when we get the tooling heated up is where you really see the results that we've got. This entire project's been based around creating a 4-meter long wing skin tool for civil aerospace. And that's what you can see on the slide here. One of the really, really big novelties from this is that this tool here has actually been cured without ever seeing an oven or without ever seeing an autoclave. It's being cured directly on the pattern block under vacuum bag using the embedded heaters that are in the tool. This has been achieved by using multiple heated zones. So they serve two purposes. First purpose is for what I just mentioned earlier. We want to be able to cure the entire tool off on the pattern block. And that doesn't just include the tool surface. We need to cure the shutter board, the sides, all the structure that makes it something that you can actually laminate onto. But then when you come to curing your components afterwards, we don't want that heated up. We don't need that heated up for efficiency's sake. We just want to heat up the tool surface. So having heated zones in there lets us do that. The other thing that we know is a massive deal in aerospace is temperature uniformity. So we want to be achieving the same plus or minus 6 degrees that we get in our autoclaves. And we've done that through a use of these heater zones and then clever placement of the insulation. And because the system is so responsive, we're very sure that we can achieve a very similar degree of temperature uniformity. I will say again, a full thermal survey is very high up on our next to-do list of tests that we want to do to instill trust in this technology. The other thing is the temperature itself. These can go to very high temperatures. In fact, we're only really limited by the glass transition temperature of the tooling material that we're using that happens to be around 190, 200 degrees. But there's no reason we couldn't go higher than that. So this is the real reason why we put this project together and why we've done this project. Curing that tool off, that 4-meter long wing skin tool, using the embedded EcoTool heaters, use 98% less energy than curing it in the autoclave. When we come to components, we're using a peak power of 1 kilowatt, which is the same as your microwave. It's absolutely, well, ridiculous, the difference in energy between the autoclave and the EcoTool system. To put it into a bit of perspective, it costs £3.60 to cure that tool off using EcoTool, where it costs over £180 to cure it in the autoclave. Now, I'm not standing up here saying that this is going to replace an autoclave, because sometimes you're going to need that 6-7 bar compaction pressure. But we mentioned earlier, there's definitely a niche for this technology in very large scale tooling, but then also leaning into the low power aspect of this. Say, for example, you do need your 6-7 bar compaction pressure. You can still use the autoclave, but maybe just as a pressure vessel, and use EcoTool in your autoclave to do the heating. You're still going to end up with a much more efficient overall system than heating all the air in the chamber in your clave or your oven. So this slide is a little map of the current work that we've done, future work that we're looking to do, and where the technology is at right now. So you've heard me mention before, currently we're doing an awful lot of testing. And that is because we want to build trust so that we trust the technology and that we can show you that technology is trustworthy. So some of that is thermal cycling, as I've mentioned. Some of that is temperature uniformity. One of the really interesting points in this technology is that by having those heater zones, suddenly you actually have more control than your oven or your autoclave. As an example, if you've got a thick laminate section with reinforcement plies, or your component may have an insulated core like a foam or a honeycomb in it, in one part of your component, you can change where your zone location is and change the power going into your zones to make sure you have enough temperature to cure that. A huge one when we're talking about out of autoclave tooling is surface finish. And we've actually achieved very good surface finish. But we're working with tooling manufacturers to get that equivalent to the kind of tooling surface that you're getting out of an autoclave. Currently, we're also still doing some optimization. We've managed to hit this massive 98% saving number, but we actually think we can do even better with a little bit more time to optimize the system. Moving forward into future work and stretch goals in this, a really lovely image would be to see an entire cure hall filled with direct heated tools and EcoTools, all plugged into power supplies. And to get there, what we need is a generalized solution. We want to be able to have a CAD of our tool or our component and to immediately understand exactly where we want our heater zones to be and where we want our insulation to be to get temperature uniformity across the entire tool. This is actually where we think AI may play a part in that, in creating that generalized solution. Another huge part, which would be really interesting to look into, would be high temperature tooling. I mentioned earlier that it's really the glass transition temperature of our tooling material that's the limiting factor in the temperatures that we can reach. But why not work with high temperature material, tooling material that is? Maybe try and use this technology to cure off thermoplastics. Lastly, life cycle assessment. I think from looking around, you've probably all seen that sustainable composites is growing, and the further we get towards net zero, 2050, it's only going to become more and more prevalent in the industry. We'd love to do a full life cycle assessment of this technology and compare it to other out-of-autoclave technologies and in autoclave and see where it stacks up and then share that data with people. I'll pass back on to Stu now just to surmise what we've gone over.
Thank you, Albert. Okay, so to summarize, EcoTool provides the ability to have unlimited size, mold tools, and components can be produced outside of their capital equipment limitations. Zonal heating to control exothermic reactions during the cure cycle on thick laminates. Also cost reduction, as Albert said, 98% savings on cure cycles. This is based on our 4-meter example, the difference between £186 and £3.60. If you're able to play this out along a typical composite tooling life of 300 cycles, this equates to an energy cost of over £54,000. That's based on our average energy rate that we're paying at Pentaxia at the moment. Also CO2 reduction, so massive savings in the amount of carbon dioxide produced per cure cycle. In our example, this is a difference between 88 kilograms and 1.76 kilograms of carbon dioxide per cure. This is based on the UK's 2023 average grid CO2 per value of kilowatt hour. Thank you for listening to us today. For more information, you can contact myself or Albert on the email addresses provided. Our website is pentaxia.com. If you've got any questions right now, I think there's a room that we can go and have a chat in straight after this presentation. Thank you very much.